Hello students, today we will see variation of molar conductivity with concentration for strong and weak electrolyte. In the last live class, I explained you that molar conductivity of any electrolyte, whether it is a strong or weak, always increases with decrease in concentration. Do you know what is the reason behind it? So lambda m always increases with decrease in concentration, no matters whether it is a strong or weak electrolyte. So if we plot a graph between lambda m molar conductivity and the concentration term, that is mole per liter, under root mole per liter, if we plot a graph, we will get this kind of curves. For a strong electrolyte like KCl, we will get this line, and for weak electrolyte, we will get this kind of curve. In both the lines, one thing is common, that the lambda m is increasing with decrease in concentration. But if you see, then you will find that there is very clear difference between a strong and weak electrolyte. For a strong electrolyte, the increment is not very much. Means when the concentration is decreasing from here to here, so the lambda m is increasing only this much. So this is almost very flat line showing a little increment, KCl. But for weak electrolyte, the molar conductivity is increasing steeply, especially at lower concentration. So this is a big difference between a strong and weak electrolyte, that there is less increment for strong electrolyte and there is sharp increment, steep increment for weak electrolyte, especially at lower concentration. So what may be reasons behind this observation? KCl is a strong electrolyte which is already 100% ionized. So its molar conductivity is increasing only due to increase in speed of ion, because there would not be very much increment in number of ions. Why? Because it was earlier 100% ionized. So there is no increase in number of ions, but there is increase in speed of ions, hence lambda m is increasing. But for weak electrolytes like CH3COH, when you dilute the solution, the two things happen. The number of ions increases and the speed of ions increases. Why the number of ions increases? Because as the dilution increases, the ionization increases. So due to two factors, number of ions increasing and speed of ion increasing, they show a steep increment, especially at lower concentration. Now, if you see, then you will find that I have extrapolated this curve. Extrapolation means that I have drawn this black line and then dotted red line. It means practically it is not possible to find molar conductivity at very low concentration, because conductometer, which is a device which measures molar conductivity, which shows its reading, it does not give very clear reading when the concentration approaches almost zero. So what we do the practical only up to a limited range of concentration, then we extrapolate the curve line. So in this red dotted line, I have extrapolated this curve, and if you see with a red dotted line, and I have met this curve to this axis. So at this axis where this curve meets, this point is called lambda m naught. It means the term for this is limiting molar conductivity. Limiting molar conductivity. So if I say that define limiting molar conductivity, so what it would be? It is the molar conductivity when the concentration approaches to zero. So this is the meaning of zero. Zero, this shows zero. So molar conductivity when concentration approaches to zero, this is called limiting molar conductivity. So it is all time possible to find a strong lambda m naught for a strong electrolyte. Now see the nature of curve for weak electrolyte. If I try to extrapolate this curve, then I won't be able to match this curve to this axis. Why? Because this curve has now become parallel to this axis. And for weak electrolyte, I can never get lambda m naught by this graphical method. So this is the limitation of graphical method, that we can find lambda m naught, limiting molar conductivity for strong electrolyte, but we cannot find it for a weak electrolyte. We can find it for strong but not for weak. Now we will see a very important law, that is Kohlrausch law of independent migration of ions. Law is simply called Kohlrausch law also. So it says that, the law says that limiting molar conductivity. So Kohlrausch found the value of lambda m naught, that is limiting molar conductivity of many strong electrolytes. Why not weak? Because weak cannot be obtained by graphical method. So he took the help of graphical method and he found the lambda m naught for many strong electrolytes, and he observed that limiting molar conductivity of any strong electrolyte, like if suppose we say NaCl, so the limiting molar conductivity of any electrolyte is equal to the sum of individual ionic conductance, So see, this is limiting molar conductivity of NaCl, that is equal to sum of ionic conductance of Na plus ion plus ionic conductance of Cl minus ion, sum of ionic conductance. Okay, so if we have to write limiting molar conductivity of electrolyte like CaCl2, so it would be equal to ionic conductance of calcium ion plus ionic conductance of Cl minus ion, and of course we have to multiply this ionic conductance of Cl minus with 2, so that we can get the total contribution, ionic conductance contribution of Cl minus ion. So for any strong electrolyte, he said that limiting molar conductivity would be equal to the sum of ionic conductance of each cation and anion. So this is Kohlrausch law. Okay. Now if we come to the application of Kohlrausch law, so very important application of Kohlrausch law is to find lambda m naught for weak electrolyte. So earlier I told you what is the drawback of graphical method, that we cannot find lambda m naught for weak electrolyte because this curve becomes parallel to this axis. It will never cut this axis. So this is the drawback of graphical method, that we can never find lambda m naught for weak electrolyte. But by using this Kohlrausch law, with the help of strong electrolytes, we can find lambda m naught for weak electrolytes. For example, if we have to find lambda m naught for acetic acid, it is a weak electrolyte. Kohlrausch law, limiting molar conductivity of acetic acid would be equal to the ionic conductance of acetate ion plus ionic conductance of H plus ion. So if we get these values on the basis of this Kohlrausch law, we can find lambda m naught for acetic acid. Now, how we will get lambda m naught? So for acetic acid, we will take lambda m naught of 3 strong electrolytes. So which would be these 3 strong electrolytes? They may be CH3CONa plus they would be HCl, and the third one would be NaCl. So with the help of lambda m naught of these three are strong electrolyte, with the help of their lambda m naught value. And from where we will get their lambda m naught value? By graphical method. We can get lambda m of acetic acid. So how we can write? We can write lambda m naught of acetic acid would be equal to what? Lambda naught. Now see, acetic acid में acetate ion आपको कहाँ से मिलेगा? Sodium acetate से. So lambda m naught of sodium acetate plus H ion कहाँ से मिलेगा? HCl से. So lambda naught of HCl. अब हमें तो ये और ये आयन चाहिए थे, ये दो एक्स्ट्रा हो गए. तो हमें क्या करना पड़ेगा, लेमडा नॉट ऑफ क्या माइनस करना पड़ेगा, NaCl. सो अकॉर्डिंग टू कोलराउश लॉ अगर हम इसको कहें कि लेमडा एम नॉट ऑफ एसिटेट आयन क्या था, दैट इज नथिंग बट द आयनिक कंडक्टेंस ऑफ एसिटेट आयन प्लस आयनिक कंडक्टेंस ऑफ Na प्लस आयन. सिमिलरली HCl क्या था, आयनिक कंडक्टेंस ऑफ H प्लस आयन प्लस आयनिक कंडक्टेंस ऑफ Cl माइनस आयन, माइनस ये क्या था, आयनिक कंडक्टेंस ऑफ Na प्लस आयन minus ionic conductance of Cl minus ion. Now, if we see that ionic conductance of Na plus, this can be cancelled with this can be cancelled with this. Now, what is left? Lambda m naught of acidic. So, we have reached to this equation. It means with the help of lambda m naught of these three strong electrolyte, we can find lambda m naught of weak electrolyte. So this is very important application of Kohlrausch law. So you will get so many numericals in your NCERT book for this. One theoretical question is this: how will you find lambda m naught of H2O? You have to think over it. H2 is also weak electrolyte. So H plus ion you will get from HCl, OH minus ion you will get from NaOH. And the remaining जो extra part हो गया वो NaCl. So with the help of three strong electrolytes, that is HCl and NaOH and NaCl. So इन सब के इन तीनों की लेमडा एम नॉट वैल्यू वो मिल जाएगी ग्राफिकल मेथड से. इनको इसको और इसको प्लस करो, इसको माइनस करो, so you can find the lambda m naught of weak electrolyte H2O. So these are the application of Kohlrausch law. Another application of Kohlrausch law is that you can find, you must understand this sign. This is alpha, degree of dissociation. So degree of dissociation for any weak electrolyte can be represented at any concentration. Lambda m molar conductivity at any concentration, or lambda molar conductivity when there is infinite dilution or when the concentration approaches zero. This is limiting. So this is very important formula, that is ionization, degree of ionization equals to molar conductivity upon limiting molar conductivity. And with the help of this alpha, you all know that in chapter solution you have also studied that dissociation constant K is equals to C alpha square upon 1 minus alpha. So you can find the dissociation constant of any electrolyte. So this is very important application of Kohlrausch law, and now you have to become well versed with the numerical problems of Kohlrausch law. So this is all about today's explanation. Thank you all.